Imagine a lump of metal the size of a bowling ball. It is light enough to float on water. It is so soft you could cut it with a kitchen knife. And yet, this single lump contains enough energy to power an electric vehicle for more than a year. That metal is lithium. For decades, lithium was a footnote in the mining industry, used mainly in ceramics, glass, and a small number of medical treatments. Then, in the span of a single generation, it became the most fought-over resource on the planet. Today, governments are rewriting trade laws over it. Companies are spending billions to secure it, and the world's two largest economies are locked in a quiet, high-stakes competition to control it. This is not just about batteries. This is about who will power the 21st century. But to understand why a single element has become the new oil, we have to go back to the moment everything changed. Why lithium matters. Lithium is the lightest metal in existence. That lightness is its superpower. When packed into a battery, lithium ions can shuttle back and forth between electrodes with almost no loss of energy. That combination, high energy density and low weight, makes lithium the ideal ingredient for portable power. For a long time, that didn't matter much. Portable power meant AA batteries in Walkmans and camcorders. The total lithium market was tiny. Then in the early 2000s, two things happened. First, a company called Tesla began building an electric sports car around thousands of small lithium-ion cells, the same kind used in laptops. Second, governments around the world started announcing deadlines to phase out internal combustion engines. Suddenly, the world needed not a few tons of lithium, but millions of tons. An electric vehicle contains between 8 and 11 kilograms of lithium. Multiply that by the roughly 100 million EVs expected to be sold annually by the end of this decade, and you are looking at a demand increase of nearly 500% in less than 20 years. That is the scale of the shift. But this raises an urgent question. If demand is exploding this fast, where will all that lithium actually come from? The EV revolution. To answer that, we have to look at the machine driving the demand. The electric vehicle is a feat of engineering, but its heart is simple. Under the floor sits a battery pack containing thousands of individual cells. Each cell is a tiny chemical reactor. When you charge it, lithium ions flow to the anode. When you drive, they flow back to the cathode, releasing energy. No combustion, no exhaust, just a quiet, efficient conversion of chemical energy into motion. For a long time, EVs were dismissed as impractical. The batteries were heavy, expensive, and slow to charge. But around 2010, the cost of lithium-ion batteries began to fall, faster than almost anyone predicted. By 2020, the cost had dropped by nearly 90%. Suddenly, electric cars were not just environmentally desirable, they were economically viable. And then, governments stepped on the accelerator. The European Union announced a ban on new petrol and diesel car sales by 2035. California followed. China, already the world's largest EV market, made electric vehicles a strategic priority. Today, automakers are racing to electrify their fleets. Volkswagen, General Motors, Ford, each has committed tens of billions of dollars to EV production, and every one of those vehicles requires a lithium-ion battery. But here's where things get complicated. The EV revolution is not just about cars, it's about the entire energy system. Solar panels and wind turbines generate electricity intermittently. To make renewables reliable, you need massive grid storage, and the cheapest, most scalable storage technology today is also lithium-ion. So, the demand is not just from cars, it's from homes, utilities, and entire national grids. This brings us to a second, more uncomfortable question. Who actually controls the lithium needed to make all of this possible?
The global map. Lithium is not rare. In fact, it is the 25th most abundant element in the Earth's crust. But it is rarely found in concentrations high enough to mine economically, and the places where it is found are highly concentrated. There are two main ways to get lithium. The first is hard rock mining. You dig up ore, crush it, and extract the lithium through heat and chemicals. This method is energy intensive, but produces high purity lithium quickly. The second method is brine extraction. You pump salty water from underground aquifers into large evaporation ponds. Over 12 to 18 months, the sun evaporates the water, leaving behind a concentrated lithium solution. This method is cheaper but slower and requires vast amounts of water. Australia is the world's largest hard rock producer. Its mines supply roughly half of all lithium globally, but most of that lithium is shipped to China for processing. South America holds the world's largest brine reserves. The so-called lithium triangle, spanning Chile, Argentina, and Bolivia, contains more than half of the world's known lithium resources. Here, the salt flats stretch for hundreds of miles, their white crust hiding brines rich in lithium. Chile has been the dominant producer in the region for decades, but Argentina is ramping up quickly. Bolivia, with the largest single deposit, has struggled to attract investment. Then there is China. China has its own lithium reserves, but they are relatively small and lower grade. What China does have is processing capacity. More than 60% of the world's lithium refining happens in China. That means even lithium mined in Australia or Chile often travels to China before it becomes a battery. So the map is clear. Resources in Australia and South America, processing in China, manufacturing in China, and then batteries shipped to Europe and North America. This geography creates a massive vulnerability. If you are the United States or the European Union, you depend on supply chains that pass through a strategic competitor. And that dependency is not just about economics, it is about national security. Which leads to the next question. What happens when the world's largest economy decides it wants to break that chain? The power struggle. In 2022, the United States passed the Inflation Reduction Act, one of the most significant industrial policies in a generation. Among its provisions was a simple rule. To qualify for EV tax credits, a vehicle's battery components and critical minerals must come from North America or a U.S. free trade partner. The message was clear. The U.S. wanted to build its own lithium supply chain, and it was willing to use taxpayer money to do it. Almost overnight, companies scrambled to open lithium projects in Nevada, California, North Carolina, and even Arkansas. The U.S. government designated lithium as a critical mineral, streamlining permits and offering billions in loans. The European Union responded with its own Critical Raw Materials Act, setting targets for domestic mining and processing. Canada, Australia, and the UK followed with similar strategies. But China did not stand still. In the years before these laws were passed, Chinese companies had been quietly buying stakes in lithium mines around the world. Today, Chinese firms control significant portions of lithium production in Australia, Chile, Argentina, and Africa. They also dominate the refining business, a position that took a decade to build. This is the new oil war, not fought with tanks, but with trade agreements, subsidies, and corporate acquisitions. And it extends beyond lithium itself. The companies that turn lithium into batteries are also concentrated. The world's top 3 battery manufacturers, CATL, BYD, and LG Energy Solution, produce more than 2/3 of all EV batteries. 2 of them are Chinese. So the West is now racing to catch up. But there is a problem. Building a lithium mine takes 7 to 10 years. Building a refinery takes 5. And the demand is growing faster than supply.
The hidden costs. To understand the cost of lithium, you have to visit the salt flats of South America. The Atacama Desert in Chile is one of the driest places on Earth. It receives less rain than any other desert, but beneath its surface lies one of the richest lithium brines on the planet. To extract that lithium, companies pump brine from deep aquifers into evaporation ponds. The water evaporates under the harsh sun, leaving behind a concentrated lithium solution. The process takes over a year, and it consumes massive amounts of fresh water, the very water that local communities and farmers depend on. In Chile's indigenous communities, tensions have been rising for years. Residents say the mining operations have lowered water tables, dried up wetlands, and threatened llama herds. Protests have delayed projects, and new constitutional debates in Chile have raised the possibility of nationalizing lithium resources entirely. Hard rock mining has its own problems. In Australia, large-scale mining consumes enormous amounts of energy. In China, refining uses chemicals that can contaminate soil and water. And in Africa, where new lithium deposits are being developed, there are concerns about labor practices, corruption, and environmental oversight. But there is a deeper environmental paradox. Lithium-ion batteries are central to the transition away from fossil fuels, yet the process of mining lithium currently produces significant carbon emissions and ecological damage. This tension has led to a growing movement around sustainable lithium. Companies are developing new extraction methods that use less water and produce less waste. Direct lithium extraction, or DLE, uses filters and membranes to pull lithium directly from brine in hours instead of months. If scaled, it could dramatically reduce the environmental footprint. But DLE is still unproven at commercial scale, and even if it works, it does not solve another fundamental problem. Because here's the twist. Even if we mine all the lithium we need, we still have to figure out what happens when the batteries die. Chapter 6. The Twist. There is a common assumption that lithium-ion batteries are endlessly recyclable. The reality is more complicated. Yes, lithium can be recycled, but the economics have not worked. For years, it has been cheaper to mine new lithium than to recover it from old batteries. As a result, recycling rates for lithium have been abysmally low, estimated at less than 5% globally. That is starting to change. As lithium prices have soared, recycling is becoming profitable. Companies like Redwood Materials in the US and Northvolt in Europe are building giant recycling facilities designed to recover lithium, cobalt, nickel, and copper from old batteries. The goal is to create a closed-loop system where batteries are made from recycled materials. But there is a catch. Recycling lithium is not like recycling aluminum. The process requires sophisticated chemical separation, and the quality of recovered lithium can vary. Moreover, the batteries we'll be recycling 10 years from now are being built today with chemistries that may be different from the ones we use tomorrow. This leads to a second twist. Lithium may not even be the final chapter. Researchers around the world are racing to develop battery technologies that do not rely on lithium at all. Sodium-ion batteries, for example, use abundant cheap sodium instead of lithium. They have lower energy density, but they are safer and much less expensive. Chinese automaker BYD has already started equipping some of its entry-level EVs with sodium-ion batteries. Solid-state batteries promise even higher energy density than lithium-ion, using a solid electrolyte instead of a flammable liquid. They could be a game-changer if they can be manufactured at scale. And then there's hydrogen. While hydrogen fuel cells are not a direct competitor for passenger EVs, they are gaining traction in heavy transport, trucks, ships, and even aircraft. The future. The truth is, no one knows exactly how the battery landscape will evolve, but we do know a few things. First, lithium demand will continue to grow for at least the next 10 years. Even if new battery chemistries emerge, scaling them to meet global demand takes time. The factories being built today are designed for lithium-ion. They will run for decades. Second, supply will remain tight. Even with new mines opening in the US, Canada, and Europe, the world will likely face lithium shortages in the late 2020s. That will keep prices volatile and make geopolitics even more intense. Third, recycling will eventually become the dominant source of lithium. Just as the steel industry now runs largely on scrap, the battery industry of 2040 will run on old batteries. But that transition is a decade away. And fourth, the competition we see today between the US, China, and Europe is not just about lithium, it is about industrial capacity. Whoever controls the battery supply chain will have a decisive advantage in the industries of the future: electric vehicles, renewable energy storage, and even consumer electronics.
For the past century, energy geopolitics revolved around oil. Oil shaped wars, determined alliances, and built fortunes. Nations without oil were vulnerable. Nations with oil held power. Now, the object of competition has changed. It is not a liquid that flows from a handful of wells. It is a metal buried in salt flats and hard rock. It requires processing, manufacturing, and technological sophistication. The countries that win the lithium race will not necessarily be the ones with the largest reserves. They will be the ones with the best refineries, the most advanced factories, and the most resilient supply chains. In a way, this is encouraging. Unlike oil, lithium is abundant. It can be recycled, and the technology that depends on it is fundamentally cleaner than the internal combustion engine. But the rush for lithium also shows that the world has not broken its habit of turning essential resources into sources of conflict. The competition is quieter than the oil wars of the past, but the stakes are just as high. A lump of metal, lighter than water, now holds the weight of the global economy. It powers the cars we drive, the grids we rely on, and the ambitions of nations. The lithium rush is not over, it has barely begun. And in the coming years, the choices we make about where to mine, how to recycle, and what technology to bet on will shape not just the energy system, but the balance of power in the 21st century. The question is not whether we will stop relying on lithium. The question is whether we will use this moment to build something better than the system it replaces. Will we repeat the mistakes of the oil age, trading one dependency for another? Or will we learn that the only lasting source of power is not control over resources, but the wisdom to use them responsibly? Only the next decade will tell.